Good morning, everybody. Thank you so much for taking time out of your busy schedules to join us today. My name is Jake Miller. I'll be your host for the morning. And today we're going to be talking about goal seeking with the AFT Arrow GSC module. This is an add-on module to AFT Arrow. So this webinar does assume some familiarity with AFT Arrow, but not to worry. We'll give a broad overview of our compressible steady state solver here today. Those of you joining us live, special shout out to you guys. Thank you so much. If you have any questions along the way, you should see a panel to the right or to the left of your screen, and there's a box in there where you can type some questions. So towards the end of the webinar, we'll go ahead and address those if you're live. So feel free to type those questions as you have them, and we'll try to get to all of those at the end here. For those of you who are joining us by watching the recorded version, thanks so much for being with us at a more convenient time for you. If you have any questions, my contact information is shown here on the screen. We don't want you to be left out, so go ahead and send those questions through an email to me and I'll be sure to address those. Thanks so much. So with that, we'll get started. Again, we're going to talk about the AFT Arrow GSC module. That stands for Goal, Seek, and Control. So a little bit about what we're going to talk about today. We're going to talk about who we are here at Applied Flow Technology. Okay, we go by AFT for short here, but Applied Flow Technology was started in 1993, and our primary focus is to develop high-quality fluid flow analysis tools on the Microsoft Windows platform. So we really work our best and our hardest in order to bring you the best products available so that you can accurately size and characterize those piping systems out there. Today, of course, we're going to be talking about compressible solvers in AFT Arrow and the add-on module for that. So those of you working with gas systems, this should be of special interest for you as well. That picture here on the screen, that's going to be our home office here in Colorado Springs. That being said, if you're ever in town or you want to attend a training seminar, we do host 3 of those each year at this office. So you'll get a chance to come see America's Mountain, Pikes Peak in the background there, and get some wonderful sightseeing in. A little bit more about AFT. For those of you who are not initiated yet, we do have customers in 70 plus countries, and we do have over 30 distributors to help us access that customer base. So if you have business in the international community and you're wondering how you can get a hold of our products, feel free to drop a question there. We're more than happy to help, and our network of distributors, very knowledgeable and very powerful in that facet. So just a couple of industries that our software is also used in. Some of these should look pretty familiar to all of those in attendance today, but we have power generation systems, aerospace, air conditioning and refrigeration systems, semiconductor manufacturing, you name it, including municipal water distribution. So a multitude of industries that we cater to through the use of all of our products, both with the AFT Arrow and AFT Fathom, and even our transient solver Impulse. So specifically regarding AFT Arrow, which is our steady state compressible solver, what makes compressible flow analysis special? Well, first off, unlike liquid systems, there's a significant velocity change in the piping for gaseous systems. So the density is also changing, and both of those are going to have a strong dependency on temperature. Now, as such, those changes are generally non-linear. So that does add a challenge to compressible flow analysis for the engineer undertaking that particular task. Additionally, gaseous flow can accelerate up to a point that we call the sonic velocity, and that leads to sonic choking when you achieve that sonic velocity. And sonic choking can very easily become a dominant characteristic of the system. Not only that, this is a little known fact, but sonic choking can occur in multiple locations throughout a piping network, in the same piping network as well. So that's a overlooked fact in industry and something to be aware of. Now you take all of those nuances and then you wrap it up into a piping network, and it can further increase the magnitude of complexity when completing that flow analysis. So AFT Arrow 6, again, that's our steady state compressible solver. We meet those challenges head on by solving all of the governing equations simultaneously. You allow the solver to do the work for you. And we also include all thermal and real gas effects. Some of our competitors overlook this, is probably the best way to say that. And so you're not necessarily capturing either the complete density change or other thermal impact that's going to change the behavior of the system. That's not the case with AFT Arrow 6. AFT Arrow 6 includes the thermal effects and the real gas effects, also known as compressibility there. So we do that by balancing mass and energy throughout the entire network, and we have our own special flow and energy balance iterative method that we use for that. And we also offer several different solution methodologies to further increase the flexibility for the user. These 6 different methods are available when in the program and very easy to navigate. We take all of that, of course, and then we wrap it up into our homegrown user interface here, and it's very easy to use, very easy to pick up, and that's our drag and drop GUI. So that makes all of that 10 times easier on top of everything. So AFT Arrow 6 does all of the legwork in a steady state fashion there, but we have an add-on module that further expands the capability of that, and that's called our goal seeking control. Just to take a moment here and pause to give you a quick idea of what the goal seeking control module is all about. Those of you familiar with Microsoft Excel's spreadsheet software, there's an add-in called the Solver add-in, and the Solver allows you to do some very simple goal seeking as well. Well, you take the power of the Excel Solver add-in and apply that to a compressible piping network, and you're starting to get into the realm of GSC. So very powerful modifier here for the base AFT Arrow 6 solver. Now the goal seeking control module, or GSC as we refer to it, allows you to answer powerful what-if questions, okay? A common example here would be what pressure reducing valve setting will result in a minimum flow rate at a downstream location, or determine the area of an orifice in order to yield a desired flow rate, okay? Doing some orifice sizing. A compressor fan speed required to deliver a required total flow for multiple users. So the GSC module will take your model and allow you to ask these questions and answer them automatically, saving you a ton of time and bringing added utility by answering these very powerful questions. Not only can this lead to reduced costs in operating, but it can also increase feasibility or the viability of a system in the first place. Now, traditionally, those questions, you might be thinking to yourself that you can answer those by hand simply by iterating back and forth. And sure, that's true enough. And often that's very straightforward when it comes to one goal and one variable. However, there is a dynamic between system components that needs to be considered. Sometimes that's overlooked, even with one goal, one variable. So the question might still be answerable by the engineer doing this by hand, by iterating back and forth. However, if you start to add more than one variable and more than one goal on top of that, then the complexity of that analysis jumps through the roof astronomically. So the goal seeking control module, not only can it handle those what-if questions, but it can do so with multi-goal, multi-variable questions. And something that would traditionally be impossible by hand, such as a 3-goal, 3-variable manual iteration while considering different dynamics between fittings in your system, goal-seeking control module, the GSC module, can handle that no problem. So we will do the iteration for you automatically. We'll use our implemented searching algorithms in order to achieve that question for you in a very efficient manner. Now, some of the capabilities of the GSC module are outlined here. Like I said, you can either have a single or multi-variable and goal what-if questions. And a good way to think about this is that it automatically determines the input value or values, if you have that multivariable question there, that will yield a desired output value. Okay, so what does my input have to be in order to get this desired result? And we can also simulate control functions based on remote sensing. So again, common question of that, what does the control valve setting need to be in order to achieve a flow rate downstream on a branch line somewhere far away? And the GSC module in AFT Arrow can definitely handle that. Now the goals that are available to you, those can be single point. You can also have a differential goal, so what is a pressure difference between two locations? Or you can have a group goal, either a max or a min, or a sum of a parameter for a multitude of lines in your piping network. All right, so before we show an example here, let's just take a quick look at what the goal seek and control module looks like. So we'll go ahead and turn on our zoom tool, and we'll do a 200 base zoom here. So in the bottom right corner, there's a button here where you can activate modules. And when you go to activate your modules, you'll see the list of available modules for AFT Arrow here, goal seek and control at the top. So if we check that, it'll look for a license and we can hit OK. This is also available from the tools menu, and then we drop down to activate modules. Again, pulls up a pop-out menu here. You can see that in the center of the screen. So we'll go ahead and we'll turn on the goal seek and control module. Again, I apologize to those of you who aren't necessarily familiar with AFT Arrow 6. If that's the case, we'd love to show you a demonstration of the software, but we're assuming some familiarity here, so I'll take some liberties in the navigation of the program there. Now, once we have the GSC module activated, you'll notice nothing inherently changes with the graphical user interface here, but if we go to the analysis menu, we'll notice a couple of different options. We'll see goal seek and control at the top, and we'll just zoom in again here for you. We'll see goal seek and control at the top. It asks us if we want to ignore or use that, and then we'll see a goal seek and control manager. So I'm going to go ahead and select use. I'll go back to the analysis menu up towards the top there, and then we'll come down to the goal seek and control manager. And this is saying that we have to have some pipes. So have to have a system in order to have a goal. All right, we'll throw some objects on the workspace here. We'll get this open. We'll go ahead and close our little magnification tool. So the goal seek and control manager pops up, and this gives you a brand new window, something completely different from the AFT Arrow 6 solver here. And you'll notice there are 3 tabs at the top. So we'll just take a quick look at each of these tabs. The first is going to be variables. Now variables, these are going to be the, think of it as the independent variable, the input that you want to change here automatically in order to achieve a desired output. So if we select new variable, it'll give us a list here, and you are not limited to the number of variables available here. You can have as many as you want or as few as you would like. You can choose which ones you want to apply, simply turning them off and on. So I have 7 here. 6 of those don't really matter, but you can choose a junction type here. So we only have an assigned pressure on the workspace here. So I'm going to go ahead and throw an assigned flow rate. We'll throw a compressor on here. We'll open that manager again. We'll add a new variable. And so we can see here that those are all available. So if we look at the assigned flow rate or the assigned pressure or the compressor, we'll see that the variable parameter here can change. So in the case of a compressor, you can change the compressor speed, the flow if it's a controlled flow compressor, the head rise here if you're doing a quick sizing sort of thing, even impeller size. If you're thinking about trimming your compressor impeller here, you can gauge that using GSC as well. So we'll just leave this on speed. We don't have any information in there, but let's look at goals. So just like variables, you can add a new goal, you can add as many as you want. In this case, the object type will either be a pipe or we can have the junctions in there as well. So if we look at the pipe, there's a whole list here of parameters that we can set as our goal. For instance, we can set the pressure stagnation, so that's going to be the total pressure. Perhaps we want that to be 50 psi absolute, and the outlet of pipe 1. So if we're trying to change the compressor speed in order to achieve a pressure somewhere downstream or upstream based on that compressor's performance, we can set it up like this. We'll hit OK, and you'll notice that a couple of objects here have added a couple of indicators. So we have G for goal and we have V for variable. So remember, the compressor was our variable and pipe 1 outlet was our goal. So on the workspace, you'll be able to see that readily through those indicators. Those indicators can also be changed if you have your own particular language that you use around the office regarding that, so not a big deal. And then finally, the last tab on the Goal Seeking Control Manager is going to be the numerical control. 9 times out of 10, there's not a need to change this, but we'll just show you some of the things going on in here. So you can change the number of optimizer iterations, the maximum number of iterations that the solver is allowed to use. The gradient calculation, that's something that is pertinent to searching algorithms here. By default, that's on central difference. If you prefer forward difference, for those of you familiar with that, you can change that. We don't recommend changing the defaults often without some background knowledge of what that's going to do. This can change the behavior of the searching algorithm, and as such could cause the solver to either land on an incorrect result if not changed properly. But if we go down here to our searching methods, we have SLP, so you can choose sequential linear programming. We also have SQP, sequential quadratic programming, and then of course the default is modified method for feasible directions. And then are the goals. We have 2 of these to choose from. One of these is relatively recent, and that's the beta method, or very common to searching algorithms, and this is also what Microsoft Excel Solver uses, is the least square method. Least square method here is going to be default, but if there is a need to change for the beta method, then that's available to you. Both of those methods have advantages that we won't get into today. The beta method, for instance, is perhaps more robust for multivariable, multi-goal, with a non-unique solution, meaning that I have 2 goals, 3 variables, different number between those 2, between goals and variables there. So we'll go ahead and we'll close out of this, and we're going to take a look at 2 simple examples. Now, these simple examples here are meant to show the utility of GSC. However, it doesn't put a full stress on GSC. So GSC will be able to handle systems much more complicated than the ones we're going to show today. The ones chosen for today's webinar have been chosen in the interest of time. So if there are any questions of whether or not GSC can handle your what-if questions, or perhaps you're interested in remote sensing for your larger models, we're definitely more than happy to answer those questions after the webinar. So the first example we'll look at is a simple heat transfer example. This is a pressure source with a known flow rate going through a 200-foot pipe with a 4-inch diameter. We have some heat transfer characteristics here. We're going to be applying a convective heat transfer model to the pipe. This is sitting in a space with ambient conditions of 70 degrees Fahrenheit with an external convection coefficient of 10 BTUs per hour foot squared Rankine. So the question initially that we want this model to answer is what is the outlet temperature for this 200-foot pipe. So we'll go ahead and build that. So we have our pressure source here. We have a known flow rate, so I'm choosing the assigned flow rate, and I'm just going to connect these with a pipe. So our pressure source here, this is all at grade, so this is going to have an elevation of 0, pressure of 0 psi-G. This is just atmospheric conditions, but it's coming in at 300 degrees Fahrenheit. So I'll hit OK to accept that, and then I'm just going to specify some information for the assigned flow rate. We know initially that this system is flowing at 1.5 pound mass per second. Elevation is already entered, so we'll just hit OK, and we are good to go. Now we'll open our pipe, and this is going to be ANSI standard steel with a nominal diameter of 4 inches, and we're going to have standard scheduling, so schedule 40. Recall that it's 200 feet long. And then on the heat transfer tab, 2 tabs over from the pipe model tab, we can select our convective heat transfer model. So the ambient temperature, again, 70 degrees Fahrenheit. And there's no insulation on this particular model, but users of AFT Arrow do have the option of choosing between 3 different insulation layers. Those can be any combination of internal and external insulation. HVAC users are notorious for using internal insulation layers there, but no insulation on this pipe, so the external convection coefficient is going to be 10 BTUs per hour foot squared Rankine. And we'll hit OK. So our 3-object model, not the most complex model on the planet. However, we're just illustrating a point here. And this system uses air. So the AFT Arrow standard fluids available to you has air as the first fluid. I'm going to go ahead and add that to the model. We're going to leave the equation of state as red light Kwong. This is going to account for those real gas effects that we were talking about earlier in the compressibility. So you've changed to a new fluid. Would you like to change all the junctions to use air? Yes, we would. All right, so the model is ready to run. We'll go ahead and we will save this. And we're just going to call this heat transfer GSC. We'll save that. And then we will go ahead and run our model. So the solution progress window, just like all AFT products, pops up. It lets you know how the solver did. We see that we have calculations complete. So we're just going to go to the output and we're going to check a couple of temperatures. So we are concerned with the temperature outlet of the system here. And there's a lot of information on the screen. We'll go ahead and zoom in on this. So we see that T stagnation, temperature stagnation outlet in degrees Fahrenheit, 128. All right, then we can get rid of our zoom tool. So determine the outlet temperature of a single pipe system. While flowing at 1.5 pound mass per second, this 200-foot pipe would have a discharge temperature of 128 degrees Fahrenheit. So simple enough, we did not use GSC there, so how could we use GSC on this system? Well, what if we determined that the operating conditions of this system has to supply a process at 100 degrees Fahrenheit exactly? So what would we have to limit the flow rate to in order to achieve that? And then as an added bonus, when we do control this pipe here, what is the heat rate out of the pipe? All right, so we'll go back to our model, navigate back to the workspace. Everything's peachy there. So on the analysis menu here, we're going to again select use goal seeking control. From the view menu, then we'll open the manager and we're going to enter the variables as shown here. So the new variable will use the assigned flow. So we're going to be changing the flow rate. A cool thing here to note is that we have the ability to bound the solver. So you can limit what the variable can go to. Perhaps you know that it's impossible for the system to supply no more than XYZ flow rate. So you can set that as your upper bound, and you can set a lower bound as 0. You have some sort of flow restriction device upstream that prevents backwards flow, so we're going to set that to 0. And then our goal here, of course, this is going to be pipe 1's outlet with a goal value of 100 degrees Fahrenheit. So let's go ahead and open that. So we have goal seeking control turned on. We'll hit use. It's going to clear our information, which is fine with us. And then we'll open the control manager. New variable, assigned flow, and we're changing the flow as the variable parameter. Everything is groovy there. Goals, new goal, pipe, and remember this is temperature, stagnation. So stagnation is how we refer to the total properties here. More easily comprehended example would be total pressure versus stagnation pressure. We use stagnation pressure. It's the same thing. It's how we refer to it here. So we're looking at the total temperature, and that has to be 100 degrees Fahrenheit at the outlet. We're going to leave the numerical control tab alone. We're going to use these defaults. We don't have any special circumstances here that require us to dive into the added utility there. So we'll just inspect our system here again. We see that we do have the variable next to the assigned flow rate. All of that information looks just fine. We didn't change any of the input, so now we are good to go. Go ahead and hit run, and one thing you'll notice, while the solution progress window is running, there's this extra bar that appeared here. For those of you watching the recorded version, feel free to go back and pause. You'll see that this wasn't here. What this is showing is the performance of the GSC, the Goal Seeking Control Solver. Now, the Goal Seeking Control Solver, when following the searching algorithm that's specified, will actually call the base solver many times. And in fact, you can see that the solver was called 69 times to be precise. Now, in using the searching algorithm, your model is turned into a mathematical equation. We call that the objective function. And the objective function is shown here by best and current. This value is set to 1,000, and the goal is to get as close to 0 as possible. So if you have a particularly complex system, or you're asking a very difficult what-if question with a varying number of goals and variables that might not be the same amount right there, then you might notice that this does not always reach 0. That's not necessarily a bad thing. This is just telling you how close to your goal you're getting. So the current box here, this shows where the objective function is on that particular iteration. Through the course of solving the searching algorithm, the AFT Arrow GSC module will vary this back and forth, and the algorithm may correct itself. So you might notice this value goes up and down, and it will continue to vary. No need to be alarmed though. The GSC module will always use your best. So we see here that the current and the best are congruent there. Things are good, and best is relatively close to 0. So now let's look at our results. In order to look at your results with the GSC module, there's 2 new tabs in the output results window here. You see GSC variables towards the top and GSC goals. You can see that if I move the mouse down, those are up towards the top here. If we click on goals, this is how close we were able to match our goal. So the input value was 100, and the actual value was 100.0. So we were able to match that. That's great news. Now the GSC variable, this is what the flow rate actually has to be in order to achieve that. So remember, we started with a flow rate of 1.5 pound mass per second, but we've determined now using the GSC solver that the value has to be 0.8857 pound mass per second. Now obviously you can round this for the sake of operation once you have confidence in that. The advantage here though is that this was done automatically. So in the next example here, we'll see that iteration is sometimes more intensive on larger models than something small like this. So sure, we could have opened the assigned flow rate here. We could have changed the flow rate to 1, reran the solver, determined that that's not good enough, vary it again, probably try 0.75, realize that we went too far, so on and so forth, and we could have honed back on that. But the solver was able to do that within seconds, and it did it almost 70 times in the amount of time it would have taken us 10 minutes or so in order to do that. So not the most complex model, but we can already start to see some efficiency that's already built in when using the GSC module. So we'll go ahead, we'll open a new model here. We'll leave the goal seeking control module on, and we are going to look at a natural gas burning system. So we have an underground storage reservoir of natural gas. We're just going to assume that's methane. We're going to assume that everything's at grade, and we are going to take into account all compressibility effects. So we're going to leave red light Kwong, all of that. Now the gas is to be supplied at 500 psi absolute and 50 degrees Fahrenheit. We have 5 parallel burners here, and each of those at 100 psi each. So the flow must be equal here. So each branch line, all 5 of these parallel lines, will have a control valve. We're going to set that control valve to 5 pound mass per second. And then we do have a heat exchanger in this system that's going to be heating this with an associated hydraulic loss. We have some piping information here. This is going to be ANSI standard steel with schedule 40 in ambient conditions of 75 degrees with an external convection coefficient of 10. And then for best efficiency of this particular process, we must ensure that the burners at a minimum deliver with a temperature of 100 degrees Fahrenheit. All right, so how much heat must this heat exchanger add to the system in order to ensure all 5 parallel burners receive gas at the same temperature, or above 100 degrees Fahrenheit? So here's a snapshot of the system. If you have access to GSC and you're following along with the recorded version, please feel free to pause, go back, here's all the information, and then you can build that system and try this for yourself. Otherwise, we'll go ahead and get started with this. So we know that we have our supply here, and that goes through our preheat heat exchanger. Slide these over. And then we know that we have 5 branch lines. So I'm going to use a trick, and those of you who use AFT Arrow on a regular basis, feel free to copy this. There's no copyright on this trick that I'll be using in order to save some time. But we will draw some pipes here. We know that we have pipes like that. Toggle this, and then we have piping down here, and we have another parallel pipe. So we'll start with the reservoir, or the tank here. We'll just call this our supply. And remember, this was at 500 psi, 50 degrees Fahrenheit, and everything's at 0 elevation. Then we have our heat exchanger. So we're going to use a resistance curve, and we're going to use a resistance curve because we have a data point for 25 pound mass per second, and we know that at 25 pound mass per second, this heat exchanger loses 10 psi. So we want to use a resistance curve because we only have that one data point, so we're going to use this fill as quadratic feature here, and we're just going to assume a second order pressure drop relationship here. We'll hit OK. And then on the thermal data here, we're going to use a specified heat rate N. We're trying to determine what this heat duty is in order to size a heat exchanger. After we have that heat beauty, then you can do due diligence, find a reputable heat exchanger vendor, and use that information in order to find the best heat exchanger for you. Now, we'll go ahead and we'll leave this field blank for now, and we'll hit OK. Then we have a branch here. This branch has 0 elevation. That looks good. And then we have a flow control valve set to 5 pound mass per second. We have to ensure that the flow is the same there. And then we have these burners at 100 psi absolute, and then the temperature is 500 degrees Fahrenheit. Now, this temperature just needs to be entered. This is a placeholder in the event that we have flow back into the system. I know from experience that won't be the case. However, we do need that initial guess if it's determined that that flow is actually in the opposite direction. So I have all 5 of these junctions specified, and we're going to move on to the piping here. This is ANSI standard steel. This particular pipe up top is a 4-inch diameter pipe, and this is 100 feet long. We'll reopen that because we are going to use a convective heat transfer coefficient with an ambient temperature 75 degrees Fahrenheit and an external convection coefficient of 10. We'll hit OK. So pipe 1 is fully specified, so this starts to allude to the trick that we're going to use in the interest of time here, but we're going to copy all of that information from that first pipe. Every piece of information, including the convective heat transfer, as simple as this. We hit all to select this, hit OK, and we'll notice that all that information is populated. So the only thing different between these 2 pipes is that this pipe is no longer 100 feet, but it is 20 feet. So we'll hit OK, and then we'll open pipe 5, and pipe 5 is actually completely identical to pipe 2. So from our drop-down menu, we'll select pipe 2, all the information, hit OK, everything's groovy, hit OK, and just like that, we've already specified pipe 5. Now, pipe 3, we'll go ahead and copy all the information, but we do have to make a couple of changes. The first change here is that this is actually a 3-inch pipe, not a big deal there, and it's only 4 feet long. Hit OK, and then pipe 4 is the exact same as pipe 3. Hit OK. And just like that, now we have everything on the workspace specified, but we're missing those 4 other sections. So if we drag across the section we would like to keep, and we press Control D, this is our duplicate feature. Duplicate also available from the edit menu. Duplicate here. This will copy not only the objects, but all of the input information in the objects. And then we can select paste, connect that, and we'll repeat this process. 3, 4, and 5. And this is the only pipe we don't need, so we'll select it and we can delete it. Then we simply need to make sure that pipe 2 is connected, and we are going to reverse the directions of these pipes just so that we don't have to look at any negative flow rates. Even though it won't change anything, we just want to make sure everything looks nice. All right, I'll get these out of the way. So now we have all 5 burners set up, and we need to ensure that all 5 of these supply at a minimum 100 degrees Fahrenheit. So let's go back to our heat exchanger on the thermal data, and we're going to take a guess of 800 BTUs per second. So if we select 800 BTUs, and we specify that this is methane, hit OK. We'll use all of that, and all of our objects are defined. Now we're ready to save this first so we don't lose all of that work. and then we can hit run. So after a couple of seconds, we have some information from our solver. We'll go to the output results. Now we could sift through all of this data on the temperature stagnation outlet column here. Right away we see that we have an 86.25 floating around. But another way to do this is on the workspace as well. If you hover over the object in question, and we're going to look at pipe 4 and pipe 16. And the reason being is these two burners are the most hydraulically distant from this branch here. So we would expect that they would receive the least amount of heat. And in fact, if we inspect this, we see that temperature stagnation outlet is 85.6 degrees Fahrenheit. So 800 BTUs per second just won't do it. Now to do that, you right click and hold. That's important. You have to hold, otherwise if you just right click, you get a menu here, not as useful as the inspection feature. So right click and hold, and then we can see all of the results here. So if 800 BTUs won't cut it for all 5 burners, let's up the ante. We'll try 900 BTUs. We'll hit OK. That clears our results, and then we'll choose to run the model again. So we're choosing intentionally, without using the power of GSC right now, to do this manually. It's not taking too long. However, this is a relatively simple model. But if we go back to our workspace, we'll inspect, and we'll see that the stagnation temperature 92. So we're getting close. If we add another 100 BTUs, we'll see what happens there. But again, it is totally possible to answer one goal, one variable by hand using manual iteration. However, this is taking a couple of minutes. In the interest of time, it'd be better to use GSC. But if I were to add any other goal or variable into the system, also knowing that I have 5 control valves and the heat coming out of the heat exchanger, that would become very quickly problematic to do by hand. So at 1,000 BTUs per second, we see that the stagnation temperature outlet is 99.6. That might be good enough for some people. I'm just going to add 5 BTUs per second just to be a stickler about it. We'll run the system. And then navigating back to the workspace, I see that I have an outlet temperature of 99.99. All right, perfect. So 1,005 BTUs per second is the required heat input for all 5 burners in order to achieve a stagnation temperature outlet of greater than 100 degrees Fahrenheit. So what we just witnessed was me manually iterating back and forth. That was only 4 iterations with the solver. Quick enough on a 16 pipe 17 junction model, but imagine, if you will, that this model was several hundred pipes, several hundred objects. So I'm going to actually look at it from the other direction. I'm going to give it a starting point of 1,300 BTUs per second, and I entered that, but I'm not going to run the model yet. I'm going to set up a goal seek for this particular model. So remember that we're going to look at the most hydraulically distant pipe, so that's going to be pipe 4, and we want to vary the heat rate from the heat exchanger. So on the goal seek and control module, under the variable type on junction type, we'll select heat exchanger, and we're going to change the heat rate. Now we'll navigate over to the goals. We'll give this a new goal, pipe, and then we need the temperature stagnation outlet of pipe 4. And this has to be 100 degrees Fahrenheit. So we turn that on. Now we see our goal. over here with this pipe and a variable there. So now we can see that they're linked. This would also be another indication for those of you that are going to use GSC for remote sensing. Those indicators there are very helpful. And we'll go ahead and run this. So you'll notice here the objective function starts to change, and that starts to drop as it approaches 0. And then you'll notice how the current does no longer match the best. However, we will use the best when the solver is actually finished. And then here we can see that the heat rate predicted by the goal seek and control variable, 988.5 BTUs per second. Very close to 1,000 BTUs per second. We could modify the searching algorithm there in order to hone that in. Perhaps we gave it a poor starting condition, so if we change this to 1100, that would give us 1,006 BTUs per second, very close. It's close initially, so those results would still be usable. Remember, most people would probably stop around 1,000 BTUs per second when they're determining that. And we can see how far off we actually were. So the goal on that run of the GSC solver was actually 98.8 degrees Fahrenheit. So that would have saved us 5 manual iterations on this, going back and forth, re-entering that. And that's just a one goal, one variable system. So with that, you can have multi-goal, multi-variable systems, which just further add to the power of the GSC module there. So what are some of the benefits of the goal seek and control module? Well, first off, you can save time. We saw that by avoiding the manual iterations. You can simulate remote sensing. So if you have control logic set up to control some downstream parameter that's very important to your operating process, goal seek and control will allow you to simulate that remote sensing capability. And then again, those multiple goal structures. I have used GSC on a consulting project for Fathom, but it still applies to AFT Arrow, where we had multi-loops in this piping network, and we had to calibrate the entire model, and we did that by setting a goal of the friction factor for the pipe by varying the pressure downstream to match field data. So we were able to calibrate a 500 pipe model using the GSC module. So very powerful tool here. And with that, those of you live, I'll go ahead and open my panel, but let's take a look at some of the questions here. All right, doesn't look like we have any questions in our box. So those of you live, we'll give you another minute or so if anybody does have a question. For those of you joining us on the recorded version, again, thanks for coming back to that. Go ahead and send an email, and I'll be sure to answer your questions that way. All right. Well, we'd like to thank everybody for joining us and taking time out of your busy schedule in order to attend our free AFT Arrow GSC webinar. We hope that this webinar was beneficial for you today. If you have any questions regarding the process of obtaining a license for the AFT Arrow 6 GSC module, feel free to shoot me an email at sales@aft.com. We would love to have that discussion with you. If you also have any questions about how to use a GSC module, more than happy to answer those as well. So with that, have fun seeking those goals out there, and thank you so much for attending. Bye.